We have a big topic today, which is linear transformations in geometry, and specifically we're focused, well, I should say mostly focused on linear transformations from R2 to R2. So we have a corresponding 2x2 matrix, and we will discuss the matrices and the transformations for scaling, rotation, shear, both horizontal and vertical shear, reflection, and orthogonal projection. Although I should say that for these two, I'm going to talk about this transformation in Rn. So from Rn to Rn. Okay, well, I think what I will do is start with these. These are maybe the most involved, and then we will get to these. And before I even start with these, we're going to go back to some geometry of vectors and dot product. And this is something that is technically in an appendix in our text, but it's important we discuss it to understand orthogonal projection and reflection and some things that are to come. Okay, well, back to the dot product. So recall, let's say V is V1 to Vn, and W is W1 to Wn. These are vectors in Rn. Okay, well, the dot product, V dot W, we just multiply each corresponding entry and add. So this is as follows. Oh. I keep writing my... It's difficult sometimes to write a V versus a W. Okay, this is the dot product. Now, some other things that come up with this, the length of a vector, or sometimes this is referred to as magnitude. Sometimes this is referred to as norm of a vector V is, this is the notation, okay? It's like absolute value, except there's two bars, or that is what the notation for it. And this is the square root of V dot V, or what you might have seen if you haven't seen it framed this way is we just take the square root of V1 squared plus V2 squared out to Vn squared. This is the length of a vector, and if you think about the vector as an arrow starting at the origin and ending at the point, this is exactly the length as you would measure it, okay, in Euclidean space. And then what else is important to say? Well, several things. The next thing I will say, and this is a theorem, is if you take the length, so for, let me say it this way, for V in Rn and C a scalar, if you take the length of CV, and this is scalar times a vector, well, this is absolute value of C times the length of V, and this is times. Okay, maybe I will just prove this for in R3, just because I can write my components all down without a dot, 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 but it really works in general. So proof in R3. Okay, so let's say that V is X, Y, Z, and then the length of CV, well, CV is, I'll write it this way, it's CX, CY, CZ. We multiply component-wise, and this would be the square root, well, hopefully I have enough space. This is the square root of CX, squared plus cy squared cz squared. Now, you notice every single term, if I square them, has a c squared. So this is square root of c squared, x squared plus y squared plus z squared. And then if you pull out the c squared from underneath the radical, you don't get c because it could be negative, but you do get absolute value of c, and then here. And this is absolute value of c times the length of v. Okay, so there's a proof in R3, but in Rn is exactly the same. Okay, so this is something that's quite important. Now, what else do I want to discuss about geometry of vectors with dot product? Well, we need the notion of a unit vector, and then I'm going to talk about perpendicular vectors, which has actually come up in homework, but I'm going to mention it now. The definition: U is a unit vector provided, and this is U in, think about it being in Rn, provided the length of U is 1, okay? And then, let's say you have any non-zero vector. For a non-zero vector, say W, we can take W divided by its length, and this is a unit vector that's in the same direction as W. As W. Well, if you think about what this says, all I've done is I take W and I multiply it by 1 over the length. So this thing will have length 1 over length W times length W, which is 1. So clearly, in light of this theorem that we proved, this vector has length 1, and I'm just scaling W by a non-negative factor. So it's still going to point the same way. It'll just be shorter or longer depending on W's length. And it's a unit vector, and this has a name. It's called the normalization. This is called the normalization of W. Okay. The next observation I want to make, let's say, I'll just say fact. It is about geometry and dot product. If you take V dot W, this is equal to, this is the length of V times the length of W times cosine theta, where theta is the angle between V and W, and it's measured between 0 and pi. So if you had two vectors that you wouldn't measure this angle, which is bigger than pi, between them, you would measure the angle here. So you can always take, if you have any two vectors, okay, whatever they are, you can take theta to be, well, the biggest it can possibly be is pi, and then the smallest it could be is 0. Okay, well, in particular, and this is something that you might do in a physics or Calc 3, something like this, you can find the angle in between two vectors by just take V dot W divided by the two lengths, and then use the inverse cosine function, for example. Okay, this is something you can do, but I am trying to make an observation for this. So what do we notice here is that, so we see that if theta is pi over 2, cosine pi over 2, this is 0, then we see, maybe I should say if, then v dot w equals 0. And a picture of this, well, what do vectors look like that have angle pi over 2 is like this. So maybe here's v and here is w. And this is the definition of two vectors being perpendicular, or another way to say it is orthogonal. Okay, so now let's do this definition. Definition, which this, like I mentioned, came up in a homework. Vectors v and w are orthogonal, or another way to say this is perpendicular, provided their dot product is 0. Now, this does say that 0 is orthogonal to every vector because, well, the length of the 0 vector is 0. It's fine. Okay, but for non-zero vectors, v and w, it says that the angle between is pi over 2. As a quick example of this idea, we see that v and w are orthogonal. Well, why? As if you take their dot product, we get 6 times 2 minus 2 times 5 minus 1 times 2. And this is 12 minus 10 minus 2. This is 0. So this says these two vectors are orthogonal. Okay, now let me just mention briefly, and I'm going to have to get my notes so that I write them down right. I will mention briefly some properties of the dot product. And again, these are all in an appendix in your text, but I'm going to be doing some things just very shortly where I might use some of these, and they're worth noting because this is definitely a topic of, dot product is definitely a topic of linear algebra. Okay, so u, v, w, vectors, k, scalar, and then the properties that I particularly will mention. I think there might be a few more in the appendix in your text, but I will mention just a few. Okay. These are the properties I wanted to mention. And most of them are pretty clear from, well, this one, I say very few things are obvious in math, but I'll say this first one is obvious because if you looked at either formula for dot product, either thinking about it as multiplying the entries, adding them up, or as the length of v, length of w, cosine theta, it's clear that you can't do it in either order. And then here are some things about if you have a constant and then the way dot product moves across a sum. Okay, so these are some properties, and there might be a couple of more in the appendix. We are ready now for orthogonal projection. Well, I'm going to talk about this in terms of Rn, as I mentioned at the beginning. Similarly, I will talk about reflection in Rn, but then we're going to look at the matrix when it's R2. Okay, so here we go. This is orthogonal projection onto a line. So we have a line L. Here it is in blue. and W is some non-zero vector, what does this mean? L is the span of W. Well, this span is terminology we will get more into later, but what it means is you take all multiples. Okay, so here is W in red. If I take all multiples, say positive multiples of W, I go out in this direction. If I took negative multiples of W, I go out in this direction, and it fills out the whole line. Here, this point here is sort of my origin, okay? And then, well, now let's continue. So for x in Rn, what I want to do is define the orthogonal projection of this vector onto the line. So we define this proj L of x, the orthogonal projection of x onto L. Maybe I'll write that. This is orthogonal, oops, I need an R. Orthogonal projection of this vector onto the line. Now another notation is like this, x, it's like parallel, it's like an equals turned on its side, but it's parallel, okay? Well, what is it in this picture? What color can I use? Green. It's like this. Well, you would just drop a perpendicular. This is now 90 degrees, and it's this, so I will do it here. This vector to here. Okay? Maybe I will move my label of my line because the line is forever. So I'll put L here. And then this green is this orthogonal projection onto the line. And there's another thing that comes here. There is this vector. Now, uh-oh, I'm out of colors. I guess I will make that also green, which goes here. And this is written this way. Okay, now we see everything in the picture. Well, what do we notice? So I will say this one also has a name. This vector, this is the component of x orthogonal to the line. And what we see, I'm going to get a formula for everything in a moment, but what do we see here? Think about addition, right? If we take this vector plus this vector, triangle rule, that is here. So we see this. This is this, the orthogonal projection plus this vector. And there's only one way to write it. This will be a unique decomposition into an orthogonal projection of x onto L plus the component of x orthogonal to L. Okay, it's a lot of words, but now let's find a formula here for this. And once we have this, then we sort of have everything else, because in particular this vector is x minus the orthogonal projection. What do we know? First of all, this x with two bars, the orthogonal projection, you notice it's a scalar multiple of w, right? Even if it went the other direction, it would still be a scalar multiple of w. So what we see here is that this vector is kw for some k, and we will find this k. This is our whole goal right now, is to find this, and then we have a formula for orthogonal projection. Okay, and then this vector, which is this minus this vector is this minus this. Very nice. This is orthogonal to w. You see it here, right? This and this orthogonal. Okay, so what am I going to do to find K? Let me get another color here. All I'm going to use is these two facts, and this will allow me to solve for K, and then I will have a formula for the orthogonal projection. Well, I'm going to use these two facts and properties of the dot product. And here, and I'll use this space to find the constant K, and then I have a formula for this orthogonal projection. Okay, well, let's start here. I know that 0 must be equal to this dotted with W. Okay, this is this statement here written as an equation. And then, well, this is this minus, and now this orthogonal projection I know is KW, okay, then dot W. Okay, well, now you might be seeing why I mentioned those properties which are in the appendix, because now I'm about to have, here's write a sum, here is a dot product. Okay, so I can write this as X dot W minus KW dot W. Okay, and technically this is KW dot W. I have parentheses here, so I have used two of those three properties. And maybe all three. The first one is sort of that you can take a dot product this way or this way. We use that all the time without even thinking. In any case, you see I'm ready to solve for K. I can just move this over this side and divide. So I get that K is equal to X dot W over W dot W. So this is the constant. Okay, this is wonderful, beautiful happiness because look, now I have this formula that the projection onto this line of X equals, here's a constant, is X dot W over W dot W, and then, well, here, times the vector W. So this is a formula which we were able to fit the work on the board for the orthogonal projection. Okay, it's a multiple of W. We see that here. And what is the multiplier? Well, it's this X dot W divided by W dot W. This is general in Rn. Now, let's do an example, and then we will get into the matrix when n equals 2. Well, here's an example. L is a line in R3 spanned by this vector. We want to find the orthogonal projection of X, and then we will decompose. Okay, so we're just seeing, do we understand the stuff we just discussed? Okay, well, first of all, I'll write it both ways, the projection onto the line of X, or we can write this as this, is, okay, it's X dot W over W dot W times W, and W is here, so times this vector, 1, 0, minus 2. Let's compute the pieces here. Maybe I will do some of that over here in blue. X dot W, okay, it's 2 times 1 plus 1 times 0 plus, minus 1 times minus 2. So this is 2 and 2 gives me 4. W dot W, this equals, well, I just dot product W with itself. This is 1 times 1 plus 0 times 0, and then minus 2 minus 2. This is 5. Okay, so this projection of X onto the line here is This is 4 over 5 times this vector, which is 4 over 5, 0 minus 8 over 5. Okay, so far so good. Well then, how do we find this part? Well, we just take x minus the projection. So this would be 2, 1 minus 1, subtract 4/5, 0, negative 8/5, and we get, well, this is 10/5 minus 4/5, we get 6/5, and then we have 1, and then this is minus 5/5, but then a plus 8/5, 3/5. Now, we should have that this part is orthogonal to W because it's orthogonal to the whole line. If you remember my picture, it's erased now, but here's the line, and here was W, and then up here is X, and then this vector is here. And you see that this should be orthogonal to W, right? So how are we going to find that out? Well, let's just check it as a sanity check. We're going to take this, we're going to dot product with W. We should get 0. And then at least what we have computed makes sense in light of what we discussed. So if we take this, we should dot W, or, well, as we know from the property, you could write W dot the other way, but this is fine. Okay, we get 6/5 times 1, and then there's a 0, and then minus, or I'll do it this way, plus 3/5 times minus 2. In fact, you see, we get 0. And the decomposition, if we want to write it out exactly, would be, maybe I'll just put a check. You don't have to necessarily do that part, but it's a nice way to see. If you've done something wrong, if I got 6 or 10 or something non-zero, I would know I made a mistake somewhere. Okay, I would like to go back to R2 now, just because I want to talk about the associated matrix. So the map that sends a vector in R2 to the projection of X, well, orthogonal projection of X onto some line, this is a linear transformation. And what we'd like to do now is find its associated matrix. And this is a big theme, I guess, in this section, is to see different types of matrices that come up when we are doing rotation, orthogonal projection, reflection, scaling, shearing, things like this. And this is our first one. The first 2 examples I will do will be the most involved, and, well, you see, here's one of them. Okay, well, what did we discuss last time? How do we find a matrix associated to a linear transformation? Well, we know that the matrix will be, if I call this, say, T, it will be T of E1 in the first column, and it will be T of E2 in the second column. This was last time. So all we need to do is apply projection to E1, projection to E2, then we have the matrix. Okay, well, again, I'm going to need the line. So to do this, let's say L is the span of, well, I'm in R2 now, so I have W1, W2. And I need to calculate T of E1. Well, this is the projection let me switch markers. This is the projection onto L of E1. If we go back to literally what we just discussed, this would be, well, it's, maybe I'll call this W. Okay, it's W dot E1 divided by W dot W, and then times W. Well, this is not too hard to calculate. We're in R2. There's only two components here, and this is E1. So what happens here? We can take this another step further. If I take, remember E1 is the vector 1, 0, and dot it with this, I just pull off the W1. Okay, and then if I dot W with itself, I get W1 squared plus W2 squared. Then I need W1, W2. Maybe I'll leave it like that for the moment. Okay, this is going to be in our first column of the matrix, but now let's compute the second column, and then we will have the matrix. It's the projection of L, E2. This is going to be my second column. And again, this is just W dot E2 over W dot W times the vector W. Okay, well now if I dot this thing with E2, E2 is 0, 1, I just get W2. So this is W2 over W1 squared plus W2 squared here. These are the two columns of my matrix. Now let's write the matrix, okay? So I'm just going to bring that all out in front. And then my first column is here. W1 squared is the 1, 1 entry, and then W1, W2 is the 2, 1 entry. So this is W1 squared, W1, W2. Now, I'm going to have to erase this part. It's still a linear transformation. I just had to erase that part. Okay, there's my first column is right here. My second column, you notice the entry is W1, W2. And the 2, 2 entry is W2 squared. This is my matrix that is corresponds to this linear transformation of projecting along a line, and is written entirely in terms of this non-zero vector along the line. If your line is the span of, let's say, U1, U2, okay, I'll write it like that, where U1, U2 is a unit vector, well, the matrix looks a lot simpler because you see this U1 squared plus U2 squared. This is just the length of U squared, right? Because the length would be square root of this. If you are a unit, this quantity here is 1. So then this is 1. So it's just U1 squared, U1, U2, U1, U2, and U2 squared. So it's a little bit simpler looking if you have a unit vector. Okay, now let's do an example. Well, here's a nice example. We want to find the matrix of the orthogonal projection onto the line spanned by this vector. And I will show you both ways that you could do it. Okay, the first way is, so way number 1, well, you take 1 over W1 squared plus W2 squared, and then here you have W1, W1, and then you have the product W1, W2, W1, W2, and then W2, well, maybe I'll write two of them, like this. This is what we found, right? And then if you multiply all this out, what is the matrix? This is 4 plus 1, this is 5, so we have, this is 1, so it's 1/5 minus 2/5 minus 2/5 and 4/5, like this, okay? Now, what's the other way you can do it? This is just working directly with this W, which is not a unit vector. The other way to do it would be, and we have the answer, and I should say that's the end of the problem if you want it to be. Now, the other way you could do this is you could just take W and create its normalization, which would be to divide by the length. So the length of W is the square root of 1 plus 4, which is the square root of 5. And then this is now a unit vector. If you take W, this is something that we discussed, right? W divided by its length, which is -1 over square root of 5, 2 over square root of 5. This is unit. And when you have a unit vector, oh, I should say A equals, okay, then I don't need this part in front, or you have it, but it's just equal to 1. So now I have a unit vector. This would be -1 over square root of 5 squared, and then this would be 2 over square root of 5 squared, and then these you just multiply, -1 over square root of 5 times 2 over square root of 5, and then this one is -1 over square root of 5, like this. Now, if you notice, what do you get? Exactly that, right? This is 1/5, this is -2/5, -2/5, and 4/5, okay? It's just two different ways of finding this matrix, and either way is perfectly fine. I'd like to discuss now reflection about a line in Rn. I'm not going to go through as many of the details as I did with orthogonal projection, but we will do some. What is reflection? Well, we saw one reflection in the last video. I reflected about the line y equals x, for example, and I will come back to it and do that example after we discuss what the matrix looks like. But we have a line, okay, which is all multiples of some non-zero vector W. So in particular, the line runs through the origin, just like when we did orthogonal projection. Well, what would be the reflection? Okay, I used to have markers that stuck together, and this would be a much better thing for this. Well, okay, here's my hands. You take this, and you just do this. This is reflection. Okay, well, what does that look like? Maybe that wasn't very clear. Now I've got to try to do as best as I can. It would be like this. Okay, you just reflect. Okay, so this is reflection here. Okay, so this is reflection. Let me write this down. Then we will figure out what it is. We want to define reflection. So this ref L of x is the reflection of x about the line L. Now, what is this? And this is why we did orthogonal projection first. So what is this? Well, let's drop the perpendicular, and now I have used all four colors again. Oh goodness. I'll just stick with green. Here, if we drop this, this is this component of x that's perpendicular to L, but now I'm going to come down again. Okay. And okay, well, so what is this? Well, I also need here. Now we will be able to see everything. There's a few ways we can write it. This is the orthogonal projection. Okay, now everything is looking really great because look, if I want this reflection, I'm actually going to write it two ways. First of all, we can take this is the projection of x onto the line, and then it's not adding, it's subtracting. So you subtract, this is minus the component of x that is orthogonal to L. Okay, so you take this, then you add minus 1 times it, so minus, and we get the reflection. We could also write this reflection entirely of x and the orthogonal projection just, well, by rearranging things. So we know, for example, that this component of x that's perpendicular to or orthogonal to the line is x itself minus the orthogonal projection. And so if we just stick that into this equation, another way to see this reflection is that the reflection is, well, put this in here. It's going to be minus a minus is a plus. You're going to get 2 here, and then minus x. Or I'll even write this another way. This is 2 times the orthogonal projection of L, or of x onto L minus x itself. The nice thing about this is, well, it's entirely just of the orthogonal projection and x, like I said. And I won't go into the details of this. I think your book leaves it as an exercise. I'll just say as a fact, you can do it as an exercise if you'd like, is that when you have from R2 to R2, the matrix has the following form. It's AB, B minus A, where, well, we will have that A squared plus B squared is 1. But how do you find these? Okay, well, because it has this nice form, you don't have to compute this for both E1 and E2. We can just find this reflection for, maybe I'll even write it that way, the reflection on the L of E1 is this. Okay, if you wanted to compute E2, it's fine, but you see, once you have A and B, you know the matrix. My first example of reflection, I want to go back to this matrix, and we saw this in Maple in the last video, that this reflected about the line y equals x. But let's see it in the framework of these calculations. Okay, well, what would the W be on the line y equals x? You can take W to be 1, 1, for example. And then the matrix A will have the form AB, B minus A, where this is, well, the T of E1, like this. I mean T as in this linear transformation, which is reflection. Okay, so how do we calculate this? Well, T of E1, it is 2 times the projection of L, projection of E1 onto L minus E1. Okay, and then now we unravel what the projection is. This would be, well, 2 times, and then the projection is, it's E1 dot W over W dot W times W, 1, 1, and then we subtract, E1 is 1, 0. Okay, this is exactly what we just found in over here and before I erased. And now we just compute two dot products and take a difference of two vectors, and we have the A, B. Okay. Well, E1 dot W is just 1 plus 0. This is 1 plus 0 over W dot W is 1 plus 1. Ooh, 1, 1. Excuse me. 1, 0. This is 2 times the half is 1. And then this is 1 here. Now we can quickly subtract. We get 0, 1. Okay, so now we can write down the matrix. This says A is 0, B is 1. So my matrix A would be 0, 1, and then B minus A. Well, ta-da! Ta-da! Oh, goodness. Sometimes I get too excited. It matches. This is what we're trying to do, right? We saw this. Now we use our theory and we see we get the exact same thing. Very nice. This is the matrix that reflects about the line y equals x. Okay, well, we know the matrix A is AB, B minus A, where if we, maybe I'll write it this way this time. Okay, so we need to compute, just like in the last example, what happens under this transformation to E1, and then we will be able to get our matrix. Okay, so reflection about L of E1 is, okay, it's 2 times the projection of L of E1 onto L minus E1. This is 2. Well, this is just like the last example, except we have a different vector that is on our line. So we have a different line. Okay, but this is E1. Now I call this W. Dot W over W dot W times W minus E1. Okay, now we just compute this. We'll take E1, which is 1, 0, dot it with this. You get negative 1. And then W dot W is 1 plus 4 gives me 5. Okay. Now we just have this number times this number, well, times this vector. This is minus 2/5 times minus 1 gives me positive 2/5. This is minus 2/5 times 2 gives me negative 4/5. But then I subtract here, and then I get, this is negative 3/5, negative 4/5. Okay, so this is my AB. Now I can write the matrix. So the matrix A, AB minus 3/5 minus 4/5, and then it's B minus A. Okay, this is the matrix that will reflect about the line that is all multiples of this vector here. Okay. Perhaps the easiest one. What is scaling, or what matrix does scaling? Again, I'm really just thinking R2 to R2 for the remaining 3. Well, we saw one. It would be K times I2, which is K, 0, 0. What this does, well, if K is bigger than Okay, technically, what do I need here? Scaling, this is for positive k. If k is bigger than 1, and then we have two different things. If k is bigger than 1, well, this is called dilation. And if k is less than 1, it's called contraction. Okay, fine. Those are just terms. What's happening is that you are multiplying this multiplies a vector by k. And we know, this is one of the first things we talked about, it's going to multiply the length. Well, k is positive here, so it's going to multiply the length by k. So if k is bigger than 1, you are stretching it out. And if k is less than 1, you are making it shorter, still pointing in the same direction because k is positive. Okay, well, that one is not too terribly hard to think about. This is the scaling. But what happens with this? With this matrix. So A, I'm going to put a negative k. Well, this is not scaling. We're not just stretching a vector or shrinking a vector, dilating or contracting, however you want to think about it. Okay. Well, let's go back to, even though we're going to do more with maple very soon, let's go back to this. And then here. What would happen here? Well, let's compute. If we take A of 1, 0, this is -1, go this way, -1, 0, 0, 0. And A of 0, 2, okay, this would be 0, 0, 0, -2. Well, okay, you see you're multiplying by -1, but maybe you could have thought about that without even writing this down. So this L is, maybe I should have not written this right below. It's fine. This one is coming down here, and this one is coming here. Just one of them. Okay, and similarly, if I had something up here, it would come down here. What you're doing, we can see, we are rotating by 180 degrees. So this one, and this is leading us into the rotations. We see what's happening, right? This L just rotated 180 degrees. So this matrix is rotation by 180 degrees, or if you think about it in radians, you're rotating by pi. Now, we saw another matrix. We saw another matrix which gives us rotation. This one. This was one of the first examples we did, that this rotated 90 degrees. And so for 180, it doesn't matter which way you think about it, but this one certainly matters. And when I talk about rotations in general, it will certainly matter. And so let's think about these as, now I have no space. Maybe I'll write it underneath. These are counterclockwise. Certainly we saw that with 90 degrees, and here, even though technically going this way or going this way would both be rotation by 180 degrees, I'm about to talk about rotation by an angle theta counterclockwise, and it's going to match for these two cases. Okay, so let's consider the transformation from R2 to R2, which is rotation counterclockwise by an angle theta. Okay? Well, what's the corresponding matrix? Let us write a unit circle. This geometry of linear transformations, I will say, as I draw my unit circle, it is so incredibly important in many applications. For example, computer graphics, video game programming, things like this. It really uses all these matrices to move things across the across the screen. So these are used. It's one of the really big applications of linear algebra is these matrices. Okay. Very nice. Let's find the matrix A, and we know the matrix A is T of E1 and T of E2. This is what we discussed last video and we have already used a few times today. All I need to do is figure out what happens to this vector here, E1. Where does that map? And figure out where E2 maps, and then I know my matrix. Okay, this is probably the most fun I've had yet today because I love trigonometry. Well, I'm rotating counterclockwise by theta. So here will be theta, and then also this one is going to move by theta. So this is theta. And this angle here is also theta, okay? This is what's happening, right? This, okay. Well, who remembers? Hopefully we remember trigonometry. This point, this is the easiest one, is this column, because this is, if I think about this unit circle, which it is, this is length 1, and I just rotate, it remains length 1. This point is literally cosine theta, comma, sine theta. That's the point, which means the vector is, well, let's write it. T of E1 is this, cosine theta, sine theta. Okay? But now this point on the graph, this is here, this vertical one is E2. So this point here is cosine, oh, I'm not going to have any space. Maybe I will just write that. This full angle is theta plus pi over 2. So let's write it here and then we'll simplify. T of E2 is, well, it's cosine of theta plus pi over 2, sine theta plus pi over 2. Now we don't want to leave it like this. We can write this in terms of cosine and sine. So if you have a sum, this is more trigonometry. This is cosine cosine minus sine sine. So this is cosine theta, cosine pi over 2 minus sine theta, sine pi over 2. And then sine theta plus pi over 2. This is sine cosine plus cosine sine, like this. Sine theta, cosine pi over 2 plus, and then cosine theta, sine pi over 2. Okay. If you don't remember these trig identities, it's okay. It's not a problem. But that's what I'm going to use. Now, the sine of pi over 2 is 1. The cosine is 0. So what we see here, this is 0, 0. This and this are 1. So now you see, what can I write? It's very simple. This T of E2 is minus sine theta cosine theta. Okay. Now I have my matrix that does rotation counterclockwise by an angle of theta. It is cosine sine minus sine cosine. So cosine theta, sine theta, minus sine theta, and cosine theta. And this matrix, when you multiply by a vector, x, y, it will rotate. So the last thing I will just mention is the shears. We have a vertical shear and we have a horizontal shear. What is a shear? Well, let's look at this. Let's look at this now. Well, we have a vertical shear and a horizontal shear, and I figured it would be best to just show you on an image. Okay, well, here is an image. This is a picture I took in the Boston Common maybe a little while ago, year or two ago. So if I shear, oh, there we go. This is shearing horizontal. This is a horizontal shear. Okay, what you notice is that horizontal shear, we have fixed, for instance, E1 has not moved, and then E2, well, it has the same height, right? This whole thing, you notice you can see the box it used to be in, the height has not changed. So E2 would still be at height, well, 1, but it's just being the x coordinate has been stretched a while, excuse me, or I could shear in the other direction. This is a horizontal shear. It will fix E1 and then E2, same height, and then the x direction is shift. So that is what would happen on E1 and E2. Will help us see our matrix. Now let's reset. Now the vertical shear, well, there's one, for example. Here's a vertical shear. And similarly, you could go in the other direction. There's a vertical shear. What you notice is that for the vertical shear, E2 is fixed. And similarly, E1, well, it's not going to be stretched at all horizontally, so the x component will remain the same, but the vertical component is what's going to move. Okay, these are the shears. So as we saw, the vertical and horizontal shear, they would, for example, horizontal shear is going to fix E1, which would give us this. But then E2 will remain the same height and be stretched horizontally by some factor. And then the vertical shear, this would fix E2. And then E1 is going to be the same height, but be stretched vertically by some factor. And here, this is for K, a constant. These are the matrices that shear, well, as we just saw in that picture. What I'd like to do now is look at just a few of the matrices that we just calculated, see what they're doing on this standard L. So we saw a few shapes last time, or a few transformations last time, I should say, before we had even talked about the geometry, but I just want to go back and look at some from this period. Okay, and I made my font bigger. I'm sorry I didn't do that last time, but now on this semester, anytime I use Maple, we will have the bigger font so everybody can see what I'm doing. First of all, this matrix A, let me make sure I typed it in right, a fifth, minus 2/5, and then minus 2/5, 4/5. This was the matrix that projected, orthogonal projection, onto the line spanned by -1, 2. Okay, and then here is the standard L in blue. And now let's look. Oh, okay, cool. What you see here, you see both of these vectors have been projected onto the same line. as it should be, right? In fact, you could even see, because minus 1, 2, and I think I'm backwards from you, but minus 1, 2 is, maybe I'll just point on the screen, is along here, right? Minus 1, 2, like that. So the E2, or 2 times E2, which is the V2, is being mapped here. And then this one is being projected down. It's being mapped to this little arrow here. Okay, so we can see, it's very nice. They're both being projected along that line. Okay, well then what did we look at next? We had the exact same vector, minus 1, 2, and we found the matrix that should reflect about the line that is all multiples of that vector. And the matrix, let me type it in. This was minus 3/5, and then minus 4/5. Okay, then minus 4/5, and then 3/5. Minus 4/5 and 3/5. Let me make sure we had minus 3/5. Okay, so this matrix should be reflecting about that line that we just projected on. Same line. There's my standard L. And now you see, well, it would be easier if I could somehow line them up side by side, but you see this L has just been reflected about a line. Okay, you see that, for instance, 0 is still mapped to 0, but it's just reflected about the line. Of course, as a side comment, we know 0 must map to 0. The 0 vector always maps to the 0 vector in a linear transformation. We discussed that last time. It's quite important. It's where we can spot why some things weren't linear transformations, because 0 mapped to something else. In any case, you see here this reflection. I hope. Okay. It's reflecting about the line that we just projected on in the first picture. Now I have some animation for you. This was fun to make. I made it last night. If you notice here, this is the first vector here is cosine t sine t. It was the first column of our matrix that rotates, okay? And then minus sine t cosine t is the second column of the matrix that rotates. Well, when t is 0, this is what's sort of plotted. This is just E1 and E2. But what I'm going to do is vary t. This is the theta. So right now it's plotting for t equals 0. This is like just the identity. There's no rotation, it's just the identity map. But I'm going to vary, you notice I'm going to vary theta between 0 and, well, approximately 2 pi. So let me do this, and then I've got to animate it. Animate. Play. And you see, now you see, look, theta. Okay, this was, let's do it again. This was, let's do continuous just for the fun of it so I could talk about it. This is what's happening as you change theta. So for any fixed theta, you would just take and move. But this is what's happening. And you see, in fact, we are rotating counterclockwise through this. Here, theta is varying. Okay, I think that's really cool. Now, there's one more thing I wanted to animate for you. But this is the column 1K, and then the column 0, 1, thinking about them as vectors. So this is going to be vertical shear. Let me stop this one. Okay. This will be vertical shear. We should be able to see it. Do we want to see continuous? Okay, sure. I only have it going from K is 0, which is the identity, to 3. But you see, and this is just acting on E1 and E2, as I was saying, vertical shear fixes E2, and then E1, I called it the height, but the x coordinate remains the same. but then the second coordinate, the y coordinate, is being stretched. So this is shearing varying k. Okay, well, I enjoy these kind of things, but also it's very good to, if we've been talking about geometry, to actually look at pictures